Now we will discuss briefly like what are the different kind of binary trees we have. First, we will discuss about complete binary tree. Okay. So let's take one example. So let us define this first. So a complete binary tree is a tree in which all levels are all levels are completely filled. Completely filled and except except optional. This is also optional. Okay. Last level. Let's let's define it in a more simpler manner. Except possibly last level where where nodes are aligned left if present. Okay. Nodes are aligned left if present. So what we are saying is all nodes, all levels are completely filled. So every level of this level of the tree has to be filled. Filled as in like it needs to have left and right child, and that's what we mean by like the level is completely filled. Every node of that level is having two child nodes, and we are saying except the last level. Last level is optional, like it can have uh, it may not have um, all the nodes of that last level may not have childs, further childs or not. And if they have, all the nodes are aligned to the left. All the nodes are aligned to the left. We'll see. So what do you think this is this first example? Is this a complete binary tree or not? So let's see. Let's start with the first level. So our with our definition, this level is consistent. It has left and right child node. What about this one? It has left, it has right, it doesn't have right. So this node is not consistent with this property. Similarly, here we don't have left node and we have right node. So this is also not consistent. So even if there is one inconsistency, a tree won't follow that property. So this is not a perfect complete binary tree. What about this tree? So this is consistent, this is consistent, and this node, although it doesn't have right node, so as of now, like so in our definition we mentioned like all the levels except last. So right now it doesn't have child, so we need to also consider that property last level where nodes are aligned left at present. So we see like there is only one node in the last level and it is aligned to the left. It is not like that if this node would have been like this, it wouldn't have been a complete binary tree. But it is aligned to the left. And let's say like if we are adding one more node here, let's say we one more node is there like this. Even in that case, all the nodes are aligned to left, and this is a complete binary tree. So two things are important here. All the nodes, all the levels are completely filled except the last level, where if the nodes are present, they're aligned to the left. Aligned to the left, when we say aligned to left, we mean to say if the nodes are present, it has to be like all the childs. It should not be the case that we have left, right, and then we don't have a left child for this, we don't have here, and we have a right node. This is not an example of complete binary tree. This will be a complete binary tree if we have one more node here left, and this can be empty as well. We have that option provision. So this is the definition of complete binary tree. We are just discussing this like because in sometime in questions directly it will be mentioned like complete binary tree or perfect binary tree. That's why like definition wise we have to be aware about this thing. Otherwise, it's not an issue with that. Now let's discuss about one more type of tree, which is called perfect binary tree. So what is perfect binary tree? Let us define that. So in perfect binary tree, all levels all levels are filled completely. All right. So only then that tree is a perfect binary tree. Let's take few example. What do we think if this is a complete perfect binary tree? What do we think if this is a perfect binary tree? If this is a perfect binary tree or not? What about first example? So we see all levels are completely filled, right? This is filled, and this is a leaf node, so this is filled. So this is a perfect binary tree. What about this? We don't have right node here, right? So this is not an example of perfect binary tree. What about this? So here also we see level 1, this level, all the childs are present. This level is a leaf, terminal level. So this is an example of perfect binary tree. So what do you think like a perfect binary tree, can it be a complete binary tree, right? So when we say perfect binary tree, is it equivalent to, can if a tree is perfect binary tree, can it be a complete binary tree? Yes, it can be, because we are saying in perfect binary tree all nodes are all levels are completely filled, and that is one prerequisite. In the complete binary tree, we mentioned like only the last node can have exception, where if the nodes are present, they are aligned completely to left. Right? So if a tree is a complete binary tree, does it implies it's a perfect binary tree as well? No. Let me give you an example. So this is a CBD, right? Where all the levels are filled, and in the last level, all the nodes are aligned to the left. But it is not a PBT, perfect binary tree, because at all the levels are not completely filled here. We don't have a child for this. It's not a perfect binary tree. So this means like all perfect binary tree are complete binary tree, and all complete binary tree cannot be a perfect binary tree. Okay. Hmm. Now, take let's discuss about the traversal of this tree. In the beginning we were saying like if we have a root node, we can possibly visit every node of that tree, right? Now let's see like how we do the traversal of this tree. So why would we want to traverse a particular tree? What can be the use case for us? use cases when we are solving our problems. So, so one use case can be process each node of a tree. Process each node of a tree for some purpose. Some purpose can which can be like which can be like calculating the salary of that particular employee, or identifying like which organization a particular employee belongs to, which organization, as in like which category of the product. And then it could be, the use case could be of search. We want to search the manager of an employee. um, we want to find the sum of the tree element, find sum of tree elements, and similarly like perform various other operation on the tree. So in the tree there are three major kind of traversal, three main kind of traversal, which we are going to look upon. One is pre-order, one is in order, and another one is post order. Okay, so all this traversal is with respect to the root node. So one easy way to create a mental map is all this traversal is with respect to the root node. Okay, so what do we mean by root node? What do we mean by this convention? So let's say in the pre-order, when we say pre-order, our root node is going to come first. We are going to process the root node first. Whatever value we have in root node, we are going to process it first. And then by convention, we will process left node and the right node, left node and the right node. So let's say 1, 2, 3, 4. So here what will happen is we will, in the pre-order manner, like we are going to, when we are at the root node here, we are going to process that node 1, and then we are going to process left node. Okay, and then when we are at the left node, right, we are going to repeat the same access pattern again. In the left node, we are going to say again like process the root node, left node, the right node. This we will take more example, but just for now, grasp this, like all this traversal is with respect to the root node of the tree. Now let's understand in order. So in the in order, what we mean by in order is like whatever order we are seeing visually. Visually, we are seeing the left, root, and the right, right? So the order will be whatever we are seeing visually, left, root, and the right. And post order. So since our traversal with is like all this convention is with respect to root, post means our root node will come in the last in a traversal. So it will be left, right, and the root. Okay. So one question will come in our mind, like hey, we are just discussing about one small part of the tree, right here, and we are not discussing about the tree can be of any manner. Like it's not going to have a perfect structure like this, and it can be very big or small, right? Tree can be of this structure or something like this. So when we observe this tree, what we will identify is like every tree is a collection of smaller trees. So everywhere we can find smaller trees in this tree. Right? So whatever boxes we are drawing, it's kind of smaller tree. for those trees. Okay. So whatever access pattern we have defined here, root, left, right, in order, pre-order, post-order, all those can be applied to the this smaller subtrees. Whatever we have problem we are trying to solve can be solve in child nodes. Solve in child nodes slash subtree. So another observation what we observe is here is like this problem is inherently well suited for recursion. When we say it is well suited for recursion, is what do we mean by that? So when we say it is well suited for recursion, we have identified there are smaller subproblems, smaller subtrees, like which is making the entire tree, right? So that's why, like, when we say it is well suited for recursion, we mean to say that, like, if we identified small problem and we solve it, we can solve the bigger problem. Let's quickly take one example where we will try to identify the pre-order, in-order, post-order of this tree. Okay, 1, 2, 3, 4, 5, and 6. Now let's try to think of pre-order of this tree. Okay, so in pre-order, what was happening? We were analyzing the root node always first. Okay, so when we start with one, we will analyze one first, and we will add it in our answer. Then we will go to our left node, and then uh, we will again analyze the root node. So in the node 2, our root node will be 2. Okay, so 2 we will add to our answer, because we we are at a particular sub problem right now. We have gone to the left side of the tree, and we again analyze in that manner, like root, left, right. Okay, so root, again our root is 2. Then we went toward again we went to the left node. We analyze the root node, which is 4. Here it is a leaf node, no left and no right. We go to the parent, we go back to the parent, and then we since we have analyzed root and left of this particular node, we will say what's the right. We will go to the right node, and in the right node we have 5. Similarly, like 5 is the leaf node, we go to the parent, and again we go to the parent, and till this point we have done root and left. We go to the right node, we analyze that particular root node, we look to the left, there is no node. Then we look to the right, there is node 6. So this forms a pre-order. Okay, now let's discuss what will be the in order of this particular tree. What was the pattern for in order? Left, root, right. We need to analyze the left node first, and then root, and then right. So easy way to build the intuition is like with respect to how you want to parse your data structure. We will come to that point as well. Just quickly, we will wrap this up. Let me put my charger. Okay. So when we say in order, we have to analyze our left node first. So when we are at 1, we went to 2, then we again ask at the 2, what's your left? We went to 4, and then we ask for what's your left? None, right? There's nothing left for the 4. Then we analyze a root node is 4, that will be added to our answer. We asked for, hey, what's your right? Nothing is there. We came back again, and then we go to the parent of 4. At the parent level of 4, we have 2, right? So we have analyzed the left part. Now we are at the root part. So starting from 2, we have analyzed the left part. Now now a root node will be analyzed. So 4, 2 again. At the 2, we ask what's your right? We went to right. Similarly, we analyzed root 5 node. Then we went to parent, nothing more to analyze. We again go to the parent. We analyze the root node 1. We look at the right. We went to the right. Again, left, there is nothing. So we again left, there is nothing. Then we analyze the root node. Then we analyze the finally the right node. Okay, so this is the in order traversal. What I want to do you as a homework is identify the post order traversal of this tree. So that will be homework. Just try to build the intuition, try to tell yourself a story like how it is happening here. Okay, now let's quickly do one. We will do one question here. We'll try to finish. We'll try to write code for our pre-order traversal. Okay. So in any recursion problem, what is important to have? In any recursion problem, so pattern, okay, so for pre-order, we have the pattern, right? Our pattern is we visit the root node first, and then left, and then right. What is the what is at what point we stop here? Like what point we stop? So when we are at a child leaf node as in like when we are at the leaf node and there is no left or right, right? That is our terminal case. So what we can say, if the node is null, then we stop our recursion. No node is null, return. Let's try to write a code for this. So let's think we are given one root node. So we will say define pre-order, pre-order, and we are given a particular node which is of type tree node, which we have discussed earlier. So it will have value, it will have left child, it will have right child. So this is the class structure of our tree node. Okay, now in a base case, we have defined a node is null, and then we return. Okay, so what we'll do, like first we will check if node if not node, which means node is null, then just return. Now in a pre-order, what we had to do was we have to analyze our root node first. So what we'll do, we will print node dot value. So we are at our root node, right? So we are at our root node. So we are printing the root node, and then what we are doing is we are recursively calling the same function again. We are saying pre-order node dot left pre-order, and then we are saying analyze the right node, and then we are concluding our analysis. Let's take one example, one small example. We have 1, 2, 3, 4. Okay, so also let's build a stack of a recursion. So this is the stack of a recursion. We are at the root node. What we do, like we start analyzing it. This is a recursion stack, right? So we are at the root node, we analyzed it, we printed 1. So this is our standard out, strictly out. We analyzed 1, and then what we did, we did the pre-order node left. We called pre-order on the left node. Okay, so we put 2 here, and then when we are at the node 2, we analyze the root node of that particular node. So what's the root node? 2. Then we try to access the left is not anything. Then we came again back to 2, and then we analyzed the root, the 4, node 4, right node. Okay, so also when we are at the node 4, we analyzed that node, that root node 4. Now left and right of 4 is none. 4 will come out of a stack, as in this routine will finish for node 4, root node 4. Okay, now we went back again to 2. We are at this point of the 2 when we are at the node, this point of the function in the node 2. All the processing has finished for the node 2. This will pop. Now we are at the node 1. The left part is done for the node 1. We will put in our stack the 3. Now 3 is a root node. We analyze the 3 node, and then we check left, right, null, nothing is there. Then our 3, this processing will finish for 3 as well. This is done for 3. This is done for 3. This is as well done for 3. So this is our pre-order traversal for this particular tree. Now, as a homework, what I want you guys to do is try post order as well. Post order. It should be, if you follow the same logic, it should be simple enough. Like, see, like root, we have done root left. Sorry. We have done root left right, right? In the this is pre. In post, we have to do left right root. Just a matter of small tweaking this order, and you will be able to do that. Just try it as homework, and then we will discuss again this. All right, so this is a starting point of tree data structure, and we will discuss more complex problem, more interesting problem as we go by. Bye guys, thank you.